Building a watch is actually quite hard. And I can't really tell you why this hobby or endeavor to design and assemble my own watch and build the tooling to build watch parts and the whole chain of events just popped up in my life, but it did, and I'm taking you along. For me, I think solving problems is a really big part of the joy, and it's my day-to-day job and my past hobbies, and it always had something to do with the element of solving problems. And this is a pretty big one. So in the last video, I turned the spindle arbor for my Watchmakers milling attachment, and this time I'm building the housing and the locking nut to finally assemble everything together and do the first run-out test. In the first step, I started just by setting up the bar stock, cleaning up the faces, the sides, so I have something to indicate on, since I'm planning to flip the whole part around. I'm starting here by center drilling, since the first thing that I want to tackle for this housing is the inside bore. I'm using a 5.6mm drill here. It's actually the biggest drill I can fit in this tiny drill chuck, but this will give me a starting point to use my smallest boring part to get to a size where I can use some serious tools. The inside bore is the most critical part of the whole design, just because in the end the two angular contact bearings will sit against the shoulder inside the housing, held in place by the spindle arbor and the locking nut, and when the concentricity is spot on, we should see minimal run out, and of course this is something we want. Here I'm measuring the ID of the shoulder. The target was 31mm, and I think we hit that quite well. Here I'm measuring the OD of the angular contact bearing. In the last video we already measured the ID, and here you can see what the target for the actual pockets is, where the bearings will sit in the end. Here I'm setting up the depth of cut for the first bearing pocket. It's 11mm, and here I'm just measuring the travel of the cross slide. And after hitting the 11mm, I'm setting the hard stop, and now we can get to boring the actual pocket. While taking off 0.1mm of material each time, I'm experimenting with the speeds and feeds of this boring bar. I didn't use it before, so in the end I want to get a nice surface finish, and this is a good moment to get a feel for it. We are slowly approaching the target size here, and I'm taking a final measurement, and yeah, at this moment I decided to just give it a go and try a test fit, and it fits quite nice. It could be a little tighter, not the typical machinist fit, but this will work out in the end. Here I'm removing the burr between the pocket and the face where the outside race of the bearing will sit, so we get a nice snug fit against the shoulder. Of course, we can't forget about the chamfering of the inside shoulder and the outside, and with a little bit of help of Scotch-Brite we will get this to a nice shine. Next up is turning the outside of the spindle housing. And in my first attempt I tried using high-speed steel, but the chip formation was, it wasn't present. So I switched to some insert tooling, and this worked out much better. While turning this OD, the heat protection of my Sherline lathe kicked in, and I guess that was a little too much for this tiny lathe, but we got it to size, so yeah, that's totally fine, I guess. After cleaning up the front face, some chamfering here and there, we are almost done with this side of the part, and let's have a look. In the next step, I flipped the part around, re-indicated it in the 4-jaw chuck to set it up for boring the pocket of the second angular contact ball bearing, and here I need 14mm of travel, and after locking the hard stop, we can get to boring. One mistake I made here was not resharpening the boring bar, and this surface finish in the end could have been a little nicer, but also this will be fine in the end. I'm struggling a little to use the telescoping gauge, and so I started just using the bearing itself as a gauge. And between the different cuts I tried again, and at this point I got it fit quite snugly inside the bore, and with this fit I'm much more happy than the first one. Like before, I'm removing the burr between the shoulder and the face, and I'm doing some chamfering of the shoulder and the outside, and in the end I'm just using some Scotch-Brite to finish up the surface. Next up is indicating the depth of cut for the front face. This was 1.85 millimeters, and just removing material one pass at a time until we hit the hard stop and leave some nice surface finish. And in the end, just using a file to remove the edge, get a nice chamfer going, and that's that. This spindle housing is almost done. We just need the mounting holes, but we will take care of them later. Let's get to turning the locking nut. The locking nut itself has two main purposes. First of all, lock the whole assembly together. So the two angular contact ball bearings and the spindle shaft against the inside shoulder of the spindle housing, and also applying the necessary preload onto the angular contact ball bearings to remove the runout and make sure that the bearings itself are not slipping. Here I'm bringing the inside bore of the locking nut to size for the tapping later. And with the help of some Scotch-Brite and a needle file, I'm getting the surface and the chamfer ready for the tapping. Here I'm setting up the parting blade to be 6.5 millimeters from the front side. So with the thickness of the parting blade of 1 millimeter, we are at 5.5 of the locking nut itself, the target size. Re-indicating the front face and the inside bore to create the last chamfer, so we can start tapping. The M17 by 1 millimeter tap I'm about to use is definitely the biggest tap I've used yet on my little lathe. And my idea was to use the life center in the tailstock to apply even pressure on the tap, so guiding it straight into the bore, and after 180 degrees of rotation, reapplying pressure from the back, and so step by step moving the tap inside of the bore. The thread itself came out pretty nice in my opinion, and what's left is just some cleanup with some Scotch-Brite, and then we can go to next step. In my initial design of the locking nut, I didn't come up with an mechanism of actually tightening the locking nut. So I need something to grip on, and I thought about a few things, but in the end I'm just freestyled it while holding the part. And what I've came up with was just two flat opposing sides with some kind of knurled face to actually grip it, and in the end I settled on using my jeweler's saw. This tool itself is definitely special to me, because in the beginning my idea was just to modify existing watches and do my own thing, and it was just me with my jeweler's saw, some needle files and some brass, and I tried to come up with something. And I've settled on designing the whole thing by myself, and Now I have a lathe and some other tools, but the jeweler saw itself will definitely have a special place in my heart because it was the beginning. And here we have the final locking nut, and it's looking quite nice, I think. The spindle itself will tackle multiple tasks. First of all, I want to be able to cut gear teeth, drill off-center holes, and finally do some light milling to actually build the watch parts I have in mind. All these different tasks need, of course, some type of specialized tooling. For example, for cutting the gear teeth, I need a fly cutter, and for the light milling work, I need some type of tiny end mill. While designing this spindle, I've decided to use a Morse taper 1, a collect, and a Drawbolt design to, in the end, hold end mills, the fly cutters, and in the future different types of tooling. In the background you can already see me turning the tiny Drawbolt, and this one in particular will be used to tighten and hold the Sherline end mill collects. The process of making this Drawbolt is quite easy. You've just saw me cleaning up the faces and the sides. I got the part where the fret will be to the appropriate OD, and here on the other side I'm just doing some finishing work to make it a little pretty, and then we can start cutting the fret. Using these dies by hand is every time quite the pain, but I'm very happy that this one turned out straight, and I got it done because the test piece I did was quite crooked, and so this one worked out, and that's very nice. And since I'm planning to tighten the Drawbolt by hand, I just applied some handmade knurling on the side, like on the locking nut, and I really like this footage, so now I'm just silent and let's enjoy it together. After finishing the Drawbolt, I did a heat treatment in the dark outside and I wasn't sure what to expect. I never heat treated anything before, and I said safety first, and so in the end I didn't produce any footage, but here you can see me tempering the Drawbolt. And I tried to aim for the dark straw color, and I hope I got it. But moment of truth, after many months of planning and designing and producing parts and scrap parts, here we are at the first test run, and I didn't really know what to expect from the run out, and I just crossed my fingers and hoped that my 0.005 millimeters of overall tolerance would produce a somewhat usable spindle in the end. Drum roll please. We have 0.005 millimeters of runout inside the Morse taper, and that's so amazing. But in the end, it's way more important how smooth the whole assembly, so a collect and a potential end mill, in this case I'm using a 4mm gauge pin, how smooth everything together is running. And I measured it, and in the end we have 0.01 millimeters of runout. And this is also so amazing, and for my first spindle I ever designed and manufactured and assembled, I couldn't be happier.